So, today I wanted to talk about infinity. So, infinity in mathematics is a very weird concept, and it's just very confusing. And so, I wanted to talk about that with some examples today. So, let's talk about an infinite number of things. So, for example, if you have a set, let's call it S, that has, I don't know, some numbers like this. So this set S has these three numbers, 1 and 3 and 7. This is very simple, right? Then we just say the size is 3 because it has 3 elements. Then what happens if you have another set? Like, let's call it T, whatever that is. Let's say we start with 1 and 2 and 3, 4, and just keeps going forever. So maybe this is related to infinity. Well, so it keeps going, but there is no number called infinity, right? Because if there was a number called infinity, like it's not like 1, 2, 3, 4, and it keeps going, and there's like, like 1,567,000,000, and the next number is infinity. It doesn't go that way. But we also have this concept of infinity where it just keeps going. So in this case, T starts with 1, goes to 2, 3, 4, and then if it keeps going, we usually say, like, intuitively, it's infinity, right? So this size is infinity. Then mathematicians started asking questions. How many different types of infinity are there? Or do we even have different types of infinity? So what that means here is this. So let's say I'm gonna create another set called U. And then earlier with T, we started with 1. But here we're gonna start with -1, -2, -3, -4, and keeps going. So if it keeps going, it's infinite, right? So this size feels like it should be infinity. And it makes sense because there is no finite number that can describe the size of this set. If you say this number only has, I don't know, 5 trillion numbers, you can find more than 5 trillion numbers in this set and then say, see, this set doesn't only have 5 trillion numbers, it has more than 5 trillion numbers. So you can't say that this has a specific number of elements because it has infinite number of elements. So the question becomes, is the size of U and T, do they have the same number of elements? And then the answer is, in a way, yes. Yes, because the way you can argue here is that if you connect the first element, and then the second element, the third element, and then fourth element, you can keep going. And you can say that, see, like, they have the exact same number of elements because you can connect them one by one. So this sort of makes sense, right? And then the next part is actually an example that somebody gave me a long time ago. And that really confused me. So let's do that. So again, I'm gonna call this one A, but actually it's the same as earlier, but whatever. 6, 7, 8, it keeps going. Nothing special here, right? And then here, I'm gonna do something a little weird. I'm just gonna drop 1, I'm not gonna do 1, and I'm gonna do 2. Then I'm gonna do 4, and I'm gonna do 6, and I'm gonna do 8. And I'm sure you all know where this is going. So this is a set of even integers, even natural numbers. So I want you to think. So they both have infinite number of elements, right? Infinite. Because it keeps going forever. But which one has more elements? So people have different reactions to this. But to me, it seemed that size of B was about half of size of A. This was my initial reaction, because the reason for that was, well, for these two elements, I only took 1. And for these two elements, I only took 1. For these two elements, I only took 1. So if you have a set of things, and if you only take half of them, the size will be, half of the original one, right? But in mathematics, at least in this area called real analysis, or just analysis, I guess, we argue that they have the same number of elements. So the argument goes like this. If you connect any elements in X with element X over 2, so if you divide an element in B, so divide by 2 and then connect them. What it means is, like, if you have 2, then what's 2 divided by 2? It's 1. So you connect it with 1. You have 4. 4 divided by 2 is not 1. It's 2. So you connect it with 2. And then 6. 6 divided by 2 is 3. So you connect it by 3. And 8 divided by 2 is 4. So you connect it with 4. And you can see that if you keep going like this, you'll connect everything in A with one element in B, and then there'll be like 1 to 1. Like one element in each set will be connected to exactly one element in the other set. So you can make an argument that size of A is the same as size of B. And in analysis, we actually call this class of infinity as countable infinite. Because it's infinite, but you can still count it. So the question is there a class of infinity where you can't even count like this? So by counting, I mean, so like set A here, we can start with 1, 2, 3, 4, so you can count that, right? But maybe there is a set of infinite things, just so infinite that You can't even count like this. There's just so many of them. Is there a set like that? Is that another big question? Um, and the answer is it's actually the set of real numbers. But I'll get to that in the next video. Thank you very much for watching, and